So I hope that you have had a chance to see your test grades because they were good. Average grade was about 80%. So very nice job on the test. If you do have questions about individual problems from the test or whatever, come see us at office hours. Everyone should have access to your multiple choice answers that you had. I'm the one that's going to, I have your actual physical tests for what scratch work did you do if you got something wrong sort of thing. Those are in my office, but everybody should be able to find your multiple choice, what you got right and wrong. Anybody that works with Math 270, all the TAs and other lecturers have access to it. It's like a spreadsheet document from the test scanner people. But in any case, they were quite good. I was very happy with that. So this that's on the board right now, this should look familiar. We talked about this last time. This is one piece of what's called the fundamental theorem of calculus. We've been kind of using the ideas of the fundamental theorem of calculus throughout the semester. It's just taken a while to get all the notation and the different ways that it's organized combined into, well, what's normally seen as fundamental theorem if you look it up. So what I mean by that is if I were to, I pulled this up a second ago, if I were to look up fundamental theorem of calculus, Wikipedia, there's a whole bunch of stuff, but formal statements of it, let's see, there's physical descriptions, here we go. So there's a couple of parts to this, and there's a lot of words in the way that they say it here, and it's written as generally two if-then statements, and I've translated those and put them into Canvas, just kind of taken out some of the words, but parts of this, some of the details of the words are things that you'll learn exactly what they all mean if you take a more advanced class, like advanced calculus or a real analysis sort of class, 400 and 500 level math courses. About the whys and hows of it mentions stuff about real valued on a closed interval and uniformly continuous. And it's like, well, okay, closed interval, got that. Uniformly continuous? That sounds kind of like we haven't really talked about that. Those are some of the smaller details that make it more proven true, more succinctly true than just kind of our idea of how we've talked about this. But this first part of the fundamental theorem of calculus says, let's see, if, after all those definitions, let capital F be the function defined in X by this statement here. So it's not quite the way in which we say it, but if I say that F, capital F of X, is this function that starts at lowercase a and goes through X, F of t times dt, that looks familiar. So this should be accumulation due to a rate, f of t, where we look at accumulation starting at a and going through x. Now what this says down here is that then the derivative of f, capital F that is f of x. Okay, so if f is defined this way, then f's derivative is this expression here. Well, that sounds a little bit weird. We had one other part in that, if you just saw from the last statement, said, well, if I have what we had written, I'll just kind of jot it next to this. Let me turn on my writing doohickey. What we had is not f of x equals this, but we started with this expression here, and we had, rather than just a f, we had r sub f of t dt. So that's kind of the notation that we were using. And we let that rate times time, this mdx expression, accumulate from a to x. And if this is the rate of change of something called lowercase f, then this tells me what accumulates between a and x. So this on its own I could say is, well, it would be f of x, except we'd have to subtract f of a. Or we also said f of x equals f of a plus this, with lowercase, all lowercase f's in our case. So they used lowercase f and uppercase f. We used lowercase f and r sub f. So the r sub was our derivative, and their derivative is this, lowercase f. So the notation is a little bit different from what we were just talking about, but we had this expression. Now thinking about this, their uppercase f is playing the same role that our just f was. And the derivative of f, we said, was r sub f. Now, this doesn't have a minus f of a anywhere in it. But if you can agree that there's some function here whose derivative is f of x, if I make a new function, let me just call it g of x. Let's say that g of x is our lowercase f of x minus our lowercase f of a. A is some number. Would you agree that g prime of x is just going to be, well, the same as this is a constant, so it'd just be whatever the derivative of that is, which, with our notation from above, that's r sub f of x, if we're using the letter x. So this part here, this f of a, when this is saying that this statement here, if I have some function whose accumulation is given by this, then its derivative is this. This is just saying kind of in a different rate. If something's accumulating at a rate given by lowercase f, there's infinitely many things we were talking about last time, this idea of there could be constants and it doesn't make a difference. So if I define something at the beginning and I know a way to accumulate that, whether or not it has a constant term in it, its derivative is nothing to do with the constant. Its derivative is just to do with this rate function here. The constant part is irrelevant in the terms of that. So let me get this scrollable again. So the second part is the more usually used for computation sort of purposes. Sometimes it's written like this, sometimes it's written like this, but it's essentially the same thing. The differences between what Wikipedia calls this corollary and this second part of the fundamental theorem of calculus are really just some of those details about continuity. So I don't want to get into the differences between those, but I'll just use this one that looks more like what we've said, just with the alternate notation from what we were just looking at. This says if f is Riemann integrable. What that means is basically it's not got weird pointy things and lots of asymptotes and stuff. So if it's Riemann integrable between a and b, then the accumulation due to this rate function here between a and b come from this capital F. Now in this case, capital F was defined to be the derivative, or capital F's derivative is little f. So again, just switching to what we had in our notation, this is more closely related to how we said this before. So if I said that f prime is going to be given by r sub f of x, so this is just defining notation, this first part. Then if I integrate r sub f of x, or yeah, dx, from a to b, I get the antiderivative of this, regular f, the thing whose rate this was, at b minus that same expression at a. Or in other words, the accumulation from a to b can be modeled in open form using a rate function, or by using the accumulation function in closed form. So how much accumulates due to this rate between a and b, it can be stated this way. Or if I know the function, or a function, any function, whose rate can be defined as r sub f of x, then this is the amount that accumulates between independent variable values of a and b, or over that interval. So we've been kind of using bits and pieces of this all along through the whole semester, but it's finally come to the part where we can make some of these closed form functions because we know enough about derivatives and rates of change. It's just a matter of remembering the relationship between these. So let's go back to this thing. All right, maybe. Here we go. So here's our statement again. The accumulation, and it can be between two specific numerical values, or it can be starting at a numerical value ending in a variable. You could actually even make a function with two independent variables and two independent variable values described like one in terms of the other. Lots of different things that could be on the integral sign here of starting and stopping point description. But this represents accumulation due to this rate function here between independent variable values of a and a general x, or we could also do from a to b, like we were just talking about, which would give a numerical value. There's a specific starting and stopping point. But this, as it's written, is an accumulation function. It has x still in it. If we were evaluating an antiderivative, we'd do this computation where I'd have a formula sort of thing minus a number. So it'd be a function of x. So the thing on the left is showing this open form, this process of accumulating change due to rates at various points during an interval. And the thing on the right is showing how we find net change if I have an accumulation or an amount function. I just compare the beginning and the end, or the beginning and a general endpoint in this case, to find net change. So if I had, and I think we took a look at this last time, a function f of x equals 3x squared minus x, just as a simple one, I know its rate of change function has the rule 6x minus 1. Or if I wanted to write an expression kind of like this, I could say, oh, let's find the accumulation from 4 through a general x. Just picking 4 at random. There's no specific meaning to 4, just my choice of something. Well, I know that this accumulates to form something of this type. And if I compare the values of this at 4 and at x, that gives me the value that I want for an answer to this integral expression. This integral expression for a specific accumulation function that begins at 4, meaning net accumulation since x equals 4. So if I have f of x minus f of 4 using this f of x, I can write an expression for that, which is a closed form way to write that amount of accumulation, which is general because it has an x in it still. Or I can describe it as an accumulation function that begins at 4 and goes through x, but occurs at this rate, 6x minus 1. So the rate varies, and the endpoint's allowed to vary as well. So if I had something like a function, an accumulation function, sine of 4x, and I believe we talked about this right at the end of class last week also. I know that its rate of change function would be a cosine function, still cosine of 4x, but then chain rule times 4. So 4 cosine of 4x. So if I saw an integral expression involving 4 cosine of 4x or anything similar to that, then I can figure out the closed form accumulation that's associated with that. And there's infinitely many, but I just have to find one. In this case, I need to figure out anything. If I want to write this in a closed form, I need to find any sort of expression whose accumulation happens with this as a rate. So this would be an example. So it's sine of 4x plus 5, sine of 4x plus pi. Add any constant you want, this would still be its rate of change. But since I'm just worried about net accumulation, the constants or starting values aren't pertinent. Those don't have an impact on it. All I'd need to know is any closed form function whose rate of change is this, and then compare its value at, in this case, not two numbers, but at the symbol value of x and at an input value of 0.1. So we just have, oops, sorry about that. Didn't mean to hit that one more time. But we just have 4 cosine of 4x, or sine of 4x minus sine of 0.4. So these, if I have a rate of change function, 3x squared, without any prompts to this, I think we talked about this also, it just says it's kind of a gimme question. What function could g of x be for its rate of change function to be 3x squared? G of x could be, thought it was going to work for a second. Has to have x cubed in it. Could have a constant, but it doesn't matter. All I have to come up with is something, so I'll come up with the simplest something I can that has a rate of change function or derivative 3x squared. And so the meaning of each of these is all about accumulation due to this rate. Or I can also think about it as net change in function g between, well, 1 and x, between -2 and x, between pi plus 2 and x. But since those all involve x, they aren't numerical amounts of change. They're just an accumulation that happens to start at a particular point. So I'd have, in this case, this should be the net change in function g between 1 and x. So final minus initial, g of x minus g of 1, which would be x cubed minus 1 cubed, which is 1. Or in this case, similarly, g of x minus g of negative 2. So x cubed minus negative 2 cubed, so plus 8. Or this here, g of x minus g of pi plus 2, which I don't want to like simplify out without parentheses, but just x cubed minus pi plus 2, quantity cubed. So all of these are accumulation functions whose rate of change is 3x squared. The derivative of any of these functions with respect to x is 3x squared. But these are each 3 different accumulation functions. This one, if I think about what's going on with this, x cubed plus 8, if I were to start at negative 2 as an x value, this would start at 0 and go, well, upward from there. If I were to start using this function, think about its values starting at x equals 1. Well, starting at x equals 1, this would be 0, and then it would increase from there. So these are net accumulation functions between 2 values, but I can also see them as, well, these are all functions whose values are 0 at this beginning spot there as an input value for x, and then, well, in this case, they're positive. They've got positive rates of change. They all and grow since that they accumulate after that initial value. So in general, though, to describe the process of all of these, of just, well, it's something related to x cubed, and I want to skip on to, sorry, I'm going to skip to where we were talking about just a minute ago. This one. There we go. So this x cubed has a rate of change function 3x squared. 3x squared has many of these antiderivatives. All of these are accumulation functions. They're all net accumulation functions that correspond to starting with no amount, like starting with amount 0 at different points. This, you can't tell from this form anymore quite as easily as from the open form, but this one starts at x equals 1, this one starts at negative 2, this one starts at pi plus 2. In terms of at that particular x value, these all have correspondingly have values of 0 as their output. So that's where we can say their accumulation begins from that point of, that's that reset at A. But each of these is described as an antiderivative of the function 3x squared. And finding antiderivatives is kind of the reverse process from finding derivatives. There are, in general, some sort of rules you could think about, kind of like derivative rules, but it doesn't work quite so easily. Just kind of like multiplication, like with large numbers, is kind of straightforward. You have a process, you carry the 1, etc. But when you do long division, there's a lot of kind of figuring, like, well, let's see, how many times does 3 go into that? And you have to do a little figuring and work it out. This antiderivative process is more like that. You have to do a little figuring, like, all right, so what could I take a derivative of that would come out kind of like the answer here, and then adjust it to make it just right. So luckily, there are many antiderivatives because constants are, irrelevant in terms of what you see in a rate function. You can't determine initial constants from that. But if you want to just describe what, as I said before, what the accumulation function has to have in it in order to have a rate like this, I can say, oh, well, this has to have an x cubed. It could have a constant, or maybe it doesn't. Maybe it's a 0 constant. But the notation for that is called an indefinite integral. There's no numbers on the sign. This is just describing in general what an associated accumulation function would have in it. So something like this 3x squared, we say that it's general antiderivative, or integrating 3x squared dx, and we don't have to worry about which letter we use because there's only numbers in the integrand, not on the integral sign also. We just say this is x cubed plus c, where this capital C is referred to as a constant of integration, but it's just there as a reminder that anything of this form, or to describe a family of functions, x cubed plus anything, would have a derivative 3x squared. So these aren't like fully fleshed out problems. It's kind of they're kind of description questions. Find something whose derivative is something like that. Oh, well, it could be something like x cubed plus any number you want. So in terms of that, let's see. Thinking about our rocket question, t to the 1.3 power was the function rule for the rate of change of the height of our rocket. And I think we talked about this multiple times earlier. So while we were talking about derivatives, if I want to describe the actual height of this, well, I don't know everything just looking at the rate of change function. All I can talk about is, in general, what the height function would have to have in it. So if the rate of change of the height after t seconds, so this is a vertical rate of change, so rate of change of the height given in meters per second. If I wanted to describe the height itself, I don't know particularly where it started. I can figure that out later. But what I can say is that, well, the accumulation of height maybe start at time 0, would have to be something of the form. Let's see, if it has t to the 1.3 power, I'm thinking of things of this form. T to the 1.3 power is its derivative. So what sort of thing would have this as a rate of change function? Well, it'd have to be t to a higher power by 1, 2.3 power because of power rule. If I have something that's a power expression with one exception, if I want to find an antiderivative, that power would be 1 larger, because when we took derivatives, the power got 1 smaller. Now, if I take the derivative of t to the 2.3 power, it doesn't come out exactly. It's off by a constant factor, not a constant additive, which we can just say, plus something. But what else do I have to have in this so that when I take the derivative of h, it comes out to be specifically t to the 1.3 power with a coefficient of 1? What else do I need in this? Yeah, a 1 over, I'm just going to put it in a normal sort of spot, 1 over 2.3. So if I take the derivative of this with, it's not a very nice coefficient, I could call it 10 over 23 to make it look prettier. But if I took the derivative of this, using power rule, this 2.3 and that coefficient of 1 over 2.3 could cancel one another out and form a 1, reciprocals. So this term would have to be in my derivative, or in my height function, in order for its derivative to be 1 times t to the 1.3 power. I need to have this term. I could have other things, and all this describes right here is a family of functions. The height function would be something like this. So if we had some initial information, like at time 0, the height of this rocket ball was such and such, so maybe the rocket ball was launched from a height of 6 meters. Sorry, just writing this kind of quickly. If I launch it from a height of 6 meters, meaning, well, its height at time 0 better come out to be 6, and then after that, it accumulates at this height. There's 2 different ways I could go about writing the actual correct height function. One, since I already wrote most of the height function, I can just say, well, make sure that at time 0, this comes out to be 6. Well, since at time 0, this is a power function, this comes out to be 0, then I'll just put a plus 6 on the end of it. That's not always how it works. It depends on what sort of function you have. But doing this, there's actually an easier way to do it in open form that doesn't involve any extra computations and figurings. It's like, oh, ball was launched from a height of 6 meters, and then after that is when it started using this rate. If we think about open form, if I wanted to write h of t in open form, I say, well, h of t starts at height 0, or starts at height 6 at time 0, and then after time 0, onward till whenever, it accumulates at this rate here. So I'm going to use, instead of t, I'm going to use something else. I'll use w to the 1.3 dw, dummy variable. But what this gives right here is, here's my r sub h of t formula. It's just r sub h of w now for symbol purposes. But I have a starting value plus what happens due to the rate, because that starting value isn't impacted by the rate. It didn't come from the rate. It's just we started at height 6, and then something happened due to this rate of change. So in a more general sense, my height at time t was given by my height at time 0 plus what accumulated after time 0 onward. So w to 1.3 dw. That's 1.3, not 1/3. So if I change this to, oh, the ball was launched from a height of 19 meters, all I have to do is change this starting value to 19. If I had slightly different information, I'm just going to erase this at the bottom. I don't want to get rid of the top part. So excuse me for a minute while I scribble some of this away. So let's say instead of being launched from a height of something, I knew something about a height at a particular point in time. So let's say that I knew that at time t equals 2 seconds, the height was 20 meters. Based on this information, it won't have risen 20 meters just based on that rate function. It must have started someplace off the ground, and if we care to figure that out, we can. But if at time t equals 2, the height was 20 meters, I can describe the height function just by knowing that. I can say, oh, well, at time 2, I have a value, and then after that, I can describe how it changed due to my rate of change. So I can just, kind of like y equals mx plus b, using the y-intercept here, or just using some other point and the rate after that. So this would be, let's see, w to the 1.3 dw still. So if I have at time 2 the height was 20 meters, all right, I'm going to put 20 here, and that's a 2 there. If it said at time 17 the height was 148 meters, at time 17 I start using the rate. Before that I had 178 to start from. So it's kind of like our y initial plus mdx, only just like in those situations we're talking about constant rate of change, y initial plus mdx, just like the equation of a line. You can start from any value and use the rate from then on, and you can go backwards as well. This one we have rate that changes all the time, so it's not a straight line going backward, but you can start from knowing any point, any xy point, 2 comma h of 2, whatever that might be. In this case it was 20 because I said so. And then use the rate to accumulate after that. Although in reality, if you used a t value that's less than 2, this would still give you the proper height at times earlier than 2. And in fact, you could substitute in 0 in that spot and find out what the starting height was. Seems kind of weird because, like, thinking about, well, integrating starting at 2 and going to 0, but what that does is essentially kind of like if you use a slope backwards. There's a positive 5 slope. Every time you go forward, you add, but if you want to go backwards, you can. You just end up subtracting. Same thing here. It's just not a constant value all the time. So if you did have a value of t, in this case, since this is a positive rate for all positive values of t, if you were to sub in a t value in this spot that's less than 2, this integral value would just come out to be something negative. Now subbing in something less than 0 wouldn't make any sense because this was a, time 0 indicated the time at which we launched the ball. So before we launched it, this rate function wouldn't apply. But you can use integral expressions, even if it looks kind of backwards, 2 through something less than 2, it just ends up subtracting the value that accumulates during that, as if like to go backwards in time in this case, to see what happened before. All right, so in any case, we've got some initial values and then accumulation afterwards. So this is a y initial plus a whole bunch of mdx's, or subtracting if it's going backward in time. All right, let's see if I can get this. So a couple of questions that aren't what I was just writing down there. So if you can write an expression just for the exact change in height between time 2 and time 5, and then evaluate that, well, more or less, you can still write it as an expression with some exponents and whatnot. You don't have to get a decimal final value sort of looking thing. But I also want to show you some GC stuff. So the expression for an exact change in height between 2 and 5 in open form, meaning involves infinitely many computations and things of that sort, just maybe an integral, adding up all the changes from time 2 through time 5 due to our rate, t to the 1.3 power, dt. And I can use t, you can use other letters too. The letters used aren't important. In this case, there isn't any conflict with using t in 2 different ways, like there were in the function expressions, writing a function for height in open form. But the value of this, since I know that h of t could be anything of the form 1 over 2.3 to the times t to the 2.3 power, you can make up something for the end. I'd need to evaluate this at 5 and at 2 to compare and find the difference or the change over that interval. But you can see that this part isn't changing. It's only this part that changes. So I don't really have to worry about what the constant might be, or if they, even if they gave me enough information, like the height was 17 at time 2. I don't have to write the plus 17 in this computation to be able to get the answer, because that 17 part isn't changing. It's the rate part, the part that has variables in it, that changes between 2 and 5. So I just need 1 over 2.3 times 5 to the 2.5, or 5 to the 2.3 power, and compare that to 1 over 2.3 times 2 to the 2.3 power, initial value. So that would be in a, here's an open form expression, here's a closed form expression. This isn't something that I'm going to evaluate by hand because I don't know how to do 2.3 powers by hand. Could estimate it by hand or something, say it's more than squared and less than cubed, but that'd be a really rough estimate. If you want to know a value for this in decimal form, you can certainly put this in your calculator. Graphing calculators, both the handheld variety and GC, are really good at evaluating integral expressions though. So if you tell it that you want it to evaluate this, you can literally just type in this expression, although it comes automatically in GC with x's built in instead of t's. You can just type in this expression and it'll give you a value. But let's take a look at that just to verify that it's doing what I said it's doing. Let's see, GC. Ooh, I'm going to clear that off of there. But integrating. So under the math, there's lots of things, but one is integral. And it gives you an integral, kind of outsized letters here, but from 0 to 1 dx. It's like, well, I didn't want 0 to 1. You can change those. I wanted 2 to 5. And it says dx. I can't change the d, well, I might be able to change the dx. I'm just going to, instead of trying to change the dx, I'm going to type in my formula in terms of x's. So this was t to the 1.3 before. I'm going to do x to the 1.3. Notice that it is the rate function that goes after the integral sign, not the antiderivative. But this says it's about 15.4747. So that would be the number of meters that the ball rises between time 2 and time 5. So what we had before when we were doing it kind of more manually, just this is a very numerical plug-in numbers and function evaluation sort of thing. GC is great at that, so is any calculator or spreadsheet or anything else. But if I look at 1 over 2.3 times 5 to the 2.3 power minus 1 over 2.3 times 2 to the 2.3 power, you can see it's the exact same result. So you can verify that you're doing the by hand sort of antiderivatives appropriately. Now, what GC won't do is it won't give you formula sorts of answers. So if you say do an indefinite integral of t to the 1.3 power, it's not going to give you 1 over 2.3 times t to the 2.3 power. But if there's a numerical sort of thing, great, it can do that. So if you know, just like any other calculator, it can evaluate those sorts of things. Those are just kind of number crunchy at some point. If you want to find the value of change between 2 points or the net change over an interval, just all you need is that antiderivative and final minus initial, but you can also, if you know the integral expression, do that in a calculator. So let's see. What I want to talk about is, if I can get this kind of slid over there. So I posted this in stuff to think about over our long weekend. There's a PDF with there's 2 sides to this worksheet. And the first is just finding a couple of derivatives. But I just want to show you as a couple of examples. So this first side says, you know, find the associated rate of change function, that is, find the derivative. So finding derivatives of things like that, that's mastery test stuff. Agreed? There's a reason for this. It's not just because we're going to take the mastery test again, because we aren't. But taking a derivative of something like this f of x involves chain rule. And to find a derivative using chain rule, you have to think about inside and outside functions or the composition. This is overall it's an exponential function. Its exponent happens to be a simple power function. So the derivative of this, derivative exponential functions are exponential functions. And if their exponent isn't just a simple variable, if it's a whole function, I have to multiply by the derivative of that, which would be, in this case, 3x squared. Or taking a derivative of something like this. This is also written as sine of x raised to the 8th power. Its derivative then, since this is an 8th power function that has an internal sine function composed in it, this would involve using our power rule, 8 times sine of x to the 7th power, or 8 sine to the 7th of x, times the derivative of our sine function, cosine. It's sine of x, so just cosine of x, no third level of chain rule. So thinking about those sorts of things, if I were to ask for an antiderivative of something like this number 1 here. So finding antiderivatives, like I said, is more about thinking backwards. What could I have started with that would land me with a derivative looking like this? If my goal is to find the original g of x, now this one we just did almost precisely, kind of a combination of an 8th power and a e to it x and e to a power function sort of thing. But what we don't get to do is product rule. I don't get to like take the derivative of one part and integrate the second part. That's not how this is going to work. I have to think of this is the result of doing a derivative. Derivatives that were the result of product rule would have like 2 large parts, and each part seems to be like shown up in the derivative of the other. This isn't that. This is 2 pieces multiplied together, where one of the pieces seems to be the derivative of something inside the other piece. Or in other words, this looks like chain rule. So trying to figure out what this came from isn't a matter of just like, oh, we'll just integrate this and integrate that and stick them back together. There's not such a thing as product or quotient rule when we're working backwards. You'd have to undo product and quotient rule, which the chances that you have that assortment of terms exactly precisely, not very likely. But if I think about integrating this, I think, well, g of x, in order for its derivative to have e to a power, the original must have had e to a power, and it has to be that same power, because when you take derivatives of exponential functions, the exponents don't change. Well, so what else would this have to have in it? Well, nothing. Because if I took the derivative of this, it'd be e to the x to the eighth times the derivative of x to the eighth, which is that. So if g prime is this expression here, then g could be anything of this form. It could have a constant on the end, or at the beginning, or anywhere else. It could have a constant term, but the only x part to this, the only term that has an x in it, would have to be e to the x to the eighth in order for its derivative to look like that g prime of x there. So what about the next one? This is a power function, not an exponential function. So in this case, g of x would have to be a power function with one higher a power of x. We just did one like this with our slightly messier exponents with our rocket. But what coefficient would I need in order that when I take the derivative of it, it looks like this? Yeah, 2. Right? So 2x to the 7th would have 14x to the 6th as its derivative, as would anything else of this form. You could have a constant added. So just looking at one other weird one from down farther on here. Let's see. How about this number 4? That's a little weird looking. The derivative of some expression ends up with cosine over 2 times the square root of sine, both of just x. I don't get to do quotient rule. Any thoughts? Yeah. Yeah, so if you remember, yeah, square roots of something. What could be in it? Square root of sine of x. So let's see. If I had a square root of sine of x, let's see if this works so far, if I need more things. The derivative of this would involve a 1 over 2 root something, same something. And then chain rule times the derivative of sine of x, which is cosine. So it's kind of this work backwards and check to see if it worked idea. There's some ways to kind of formalize this that are helpful if the derivatives that you're looking at, or integrands, if it's written as an integral problem to complete, are a less precise match. If it's a little bit harder to see, like if this hadn't been a 2, if this had been like some like 7/3 and there's maybe like a negative or something thrown in there, like, oh, this is a mess. There's some ways, and you'll learn about more of that in calculus 2. You'll spend a bit of time dealing with some other techniques for integrating, techniques for finding antiderivatives or working backwards from a derivative to find an accumulation function whose rate you know. Some things can't be found precisely, like for instance, if I said that f prime of x is e to the x squared, and that's it. Well, if I figure out, well, what could that be the derivative of? Well, it'd have to be something with an e to the x squared, so that its derivative would have e to the x squared, but anything that with an e to the x squared would have a times 2x, and this doesn't have that. So it doesn't work very well. Not every function is directly a simple derivative of a nice other function, so there's a lot of techniques for how do I deal with something like this then? Well, if I needed to know what f is, one way you could do it is write it in open form. F of x would be an integral from anything you want to x of e to the, let's call it t squared dt. There we go. This is an antiderivative of e to the x squared. I haven't written it in closed form, but this expresses the accumulation due to that rate whose accumulation function, I don't quite know what it is or how to write it. I can write it this way. So that's what we did earlier on before we talked about derivative rules. If I want to know how much accumulates due to a certain rate, if you don't know how to write the accumulation function in closed form, don't. Write it in open form. Use an integral notation to express that. And there are lots of techniques for how to rewrite functions to be able to express them in a different form that's less weird. But for any numerical values, even though we can't get this in a closed form right now, there's whole 400 and 500 level classes on how to write things to approximate them with polynomials is even something you can talk about a little bit in calculus too. But something like this, even though I can't evaluate this myself right now, I can get for numerical values of x here. So if I wanted to know a net change between two values, I can use technology to find that amount as long as I know that this is the expression that tells me how function f accumulates. So, like I said, there's not everything is impossible, but I just wanted to point out something that's a little bit weird. And the rest of the questions on this sheet where you're supposed to be finding antiderivatives, some of them are maybe easier than others. There's some more with square roots and 2 times square roots in the denominator. We'll talk about these on Tuesday next week, but the idea is this kind of thinking backward about how derivatives work, and most of these involve kind of this chain rule, undoing chain rule mentally. So to figure out, well, what else would have been multiplied on this? If I took a derivative, can I adjust maybe the coefficients or constant multiples to make this come out just right? So let's see. One other thing that I wanted to start on today, and we'll continue with next week, is another way to see or use the fundamental theorem of calculus, which, let's see, we've talked about most of this. There we go. Oop, I lost my writing thing. Hold on a sec. There we go. So this looks a little bit weird. I've got an integral expression with a derivative in front of it. So in a sense, you can kind of think of this as related to like, well, I did multiplication and I did division, or I squared something and I took a square root. In some sense, derivatives and integrals are opposites, but there's some other things in between here, namely the 4 and the 7, that make this not quite just like I did something and then I undid it. So my answer isn't just sine of 3 cosine of x, or something like that. So looking at this expression, you need to look at it and think, well, what does this mean? That'll help you interpret what you need to do with this. So when you see, kind of start from the inside and work out, we have, as you can see, this function here times dx. I can think of, oh, this is a rate of change times a dx, or this part here measures little bits of accumulation. And then I'm going to let it accumulate between 4 and 7. And then I'm going to take a derivative of that. Well, it's not a function, it's an amount. So if you look at something like this, notice that this integral from 4 to 7, that would have some sort of numerical value, like it's 12, maybe it's negative 4.8, whatever it is, but it's some sort of number, right? Because that's how much accumulates or deaccumulates, it could be negative, between 4 and 7 as x values. So this is all a number. What happens if you take the derivative of a number? 0. Answer to this one is 0. Now, not every question like this is going to be something related to 0. This one, though, has just as messy a rate function. You try to think like, well, what function has this as its derivative? Sine of 3 cosine of something? I'm not really sure. So let's imagine that we know what it is. And we can get a long way with just symbols and thinking about things, even if I don't know how exactly this accumulates. I know that in this question, that in this case, this is just representative of some number. And if I take the derivative of some number, it's 0. Now in this case, it's not a number. It's from 4 through x. So, I don't know, let me say that this is called r sub f of t. So, meaning it's the rate of change function for some mystery f. Do I know what f is? No. But if I did, I'd evaluate this by finding f at x and f at 4 and subtracting. And then there's only one, so that's this part of it is f of x minus f of 4, just symbol-wise. So now, if I want to take the derivative of f of x minus f of 4, well, the f of 4 part is just like above, I'm going to get, well, let's see, how do I take the derivative of f of x? I don't know what f of x is, but I could write it symbolically as r sub f of x, and then this part's a 0. It's a number. F of 4 is some number. So r sub f of x. Oh, well, here's r sub f of t. So even though I don't know what f is, my answer I can get anyway. Sine of 3 cosine of x. This is f of x. This one is f of t. So this one is just an example of, well, I integrated and then I took a derivative. There was an extra constant that showed up in the middle, but I just took the derivative of that constant also, so it went away. The idea, though, is to know what it is you're looking at. If you can interpret it, the notation looks crazy. It's like, what on earth is this asking me to do? But if you think through from the inside to the outside, you can come up with ways to express what the answer is, even without, like in the case of this, knowing how to find an antiderivative for sine of 3 cosine of x. I don't know what the antiderivative of sine of 3 cosine of x is either. So this is a harder variety of this question. We're looking at a derivative of an integral, where the integral is from -5 through not x, it's e to the 4x. So we'll do some more examples like this next week. But if we kind of use the technique of before, we can do mostly the same thing. So I'm going to give you a couple minutes, see if you can try to follow what we did the last time and come up with a way to write at least part of this. And we'll finish it up together. But I want the derivative with respect to x of the accumulation due to this rate square root of 1 plus w squared. Another one of those, can't really integrate it directly because nothing would have that as its derivative. But this rate evaluated between -4 and e to the 4x are allowed to accumulate between -5 and e to the 4x. And then a derivative with respect to x of that. So thinking symbolically about what the pieces are, we can simplify the notation related to taking a derivative of an antiderivative. looking at this last one here, if I've got an integral of something. So this function that's in the integrand, the function that is listed after the integral sign, I can think of this as a rate of change of something. Even if I don't know what that something is in closed form, let me call it the rate of change of function f. So r sub f of w in this case, since it's got w's in it. Well, that means that if I were able to find an antiderivative, it would be comparing two positions in function f. So f, not of x, but f of e to the 4x minus f of negative 5. That's this integral part of it. And then we still need to take a derivative with respect to x. So this is a constant just like before, so the end part's easy. Derivative of f of negative 5, whatever it is, it's some number. The derivative of f of e to the 4x. Well, looks like we've got a chain rule. The inside part is e to the 4x. Outside I've got function f, this mystery function. So to take a derivative with chain rule, I'm going to leave the outside, or take the outside's derivative, leaving the inside alone, and multiply on as a second factor the derivative of this inside function, which would be, well, really chain rule again, but 4e to the 4x. The derivative of e to the 4x is e to the 4x times 4. Or, using our other notation, this is r sub f of e to the 4x times 4e to the 4x. And r sub f was just this square root expression. So to write this back in the, without mystery notation f here, r sub f, well, this is r sub f. It was a square root of, r sub f of w is the square root of 1 plus w squared. R sub f of this is going to be 1 plus e to the 4x squared, and then times 4e to the 4x as a separate factor. So without knowing how to find an antiderivative of square root of 1 plus w squared or square root of 1 plus whatever squared, we can still find the derivative of that antiderivative, because those are actually inverse operations. So we can symbolically write the antiderivative and then take the derivative going back to our original. It's just that there's another step in between that in this case led us to need chain rule to take that derivative. If this had just been a simple x on the integral sign, it would have ended up just like the last one did, just the answer being the expression inside the integrand, just with an x instead of a w or a t or whatever other letter. So sometimes questions like this are called using the fundamental theorem of calculus, but in reality it's using calculus. It's using our facts. So all of these relationships between accumulation and rate of change, just make sure you know the symbols and the notation that go with it, and think about them when you see them, so that when you encounter a slightly weird combination of pieces, we can work our way through that. Now, what I did want to mention about stuff like this, there's a lot of, like I said, in Calculus 2 you'll talk about some more ways to deal with how do I integrate something that I don't know as the derivative of a simple function. Like I can't come up with something whose derivative that looks like that. A lot of the times what it ends up being is kind of changing variables, and in cases with square roots, sometimes it ends up like draw some triangles and write some stuff about trig instead. If I had 1 and w as sides of a triangle, this would represent the length of the hypotenuse, which maybe you could write in terms of sine and cosine and angles and stuff instead. And sines and cosines and angles are much easier to take derivatives of. So it's lots of times it's just trickery with like, oh, well, I don't know what this is right here, but I can change some variables and then make it into something else that I do know. And that's most of the trick of math, like make something look like a problem that you've already done before. It's just that the more math you know, the more ways to change things there are. There's more different interrelationships that you could be familiar with. But for today, I'm going to stop at that. Again, if you have questions about your test, stop by office hours. Your last recitations that are remaining are going to be kind of wrap up, talk about fundamental theorem of calculus and all these rates and accumulation and antiderivatives. We'll do some more just general practice with antiderivatives next week and talk about your final and kind of a more comprehensive overview of what we've done over the semester, since it's a lot of things. All right, in the meantime, be nice to your family and eat a lot of food. Have a good Thanksgiving.